Good afternoon, everyone. It is actually an unusual time for me to be doing this stream. I'll tell you why. This morning I did the stream at the usual time at 9:30 in the morning, and I had a few of my students on Zoom, I had some people on YouTube, and I actually totally forgot to press the record button on both the Zoom and the YouTube stream. And so I did the whole thing without without recording any of it. And I also wondered why the people on YouTube weren't saying a whole lot, and it turns out because they couldn't see anything I was doing. So here we are at 1 o'clock in the afternoon, same day, but I'm going to redo the entire session just for you. So as far as people on YouTube, I know it's a little bit later than it normally is. It's what, 3.5 hours after I'd normally be doing my stream. And so some of you, unfortunately, have probably already gone to bed. So you'll unfortunately have to watch this on the replay, but maybe this time we'll get some different people on here. So why don't we go ahead and get started? And today we're talking about, well, let me set the stage here. Last week we were talking about basic encryption and decryption using really simple ciphers like the shift cipher and the linear cipher. And we established the foundation of terminology about things like modular arithmetic and the totient function and multiplicative inverses, and being able to do things in Python with the lambda function, and being able to filter and map. So all of that stuff is laying the groundwork for what we're doing this week, which is modern cryptography, the kind that you see on your web browser when you browse to a website and you see that little lock icon in the address bar. That means that your transaction between your browser and the web server is encrypted, and it's using one of these modern cryptographic techniques that we're going to go over. So why don't we just dive right in and we'll start talking about that. So first thing is symmetric key cryptography. That's the kind of cryptography that the shift cipher and the linear cipher were. They use a shared secret key. So that means both the sender and the recipient use the same secret key to both encrypt and decrypt. As far as modern ciphers go, we got 3 of them that I'm going to mention. One of them is called DES, the Data Encryption Standard. That one actually was developed, I think, in the 1970s, and it's not used so much anymore because it's a simple compared to the other ones, a simpler encryption standard that uses fewer bits in the secret key, and therefore it is easier for modern contemporary computers to crack that key, even by brute force, by trying all possible keys. They can eventually get it. It's only 56 bits long, which means a modern computer can go through that probably in a matter of just a few hours, can try all the possibilities, and eventually stumble across the correct key. So DES, not used as much these days. There's another one called 3DES, and the one that is used most often these days is AES, the Advanced Encryption Standard. So it's not only used to protect internet transactions, it's also used to encrypt files on your computer, and also the entire disk. You probably on your operating system have the option to encrypt your entire disk, and that makes it so that people who don't know the unlock code for your computer unable to see the contents of the disk. Same thing's going on with your cell phone these days. Usually when you set up your phone, it's either a default option or it's one of the options when you set up your phone whether you want to encrypt all the data on the phone, and it works the same way. When you unlock your phone, when you type in your unlock code or you use your thumbprint or you use your face identification, that essentially is the secret key that is used to encrypt and decrypt the data that's on your device. Symmetric key cryptography also happens to be faster than the other kind we're going to talk about, which is public key cryptography. And so right here, symmetric key ciphers are fast, And often there is dedicated hardware on your computer that is used to encrypt and decrypt AES. So even like modern phones, modern processors might actually have a section of the processor set aside specifically to do AES. So it's really fast because it's done in many cases in hardware. There was an incident a few years ago, happened in Southern California here in the United States, where somebody, I don't remember the exact details, but there was like a shooting, and it was the FBI, the police had to investigate the shooting, and they thought that there was some good evidence on the suspect's phone, and it was an iPhone, and the entire storage was encrypted on it, and so the police wanted to get access to it. Now, as I said a moment ago, you type in that access code, and that basically unlocks the phone. It gives access to the storage device and all the data on it. But the way the iPhone is set up, you only have 10 tries to type in that ID code, your unlock code, and if you fail on that 10th try, it then throws away the encryption key, and then you are unable then to unlock the phone, and you're unable to get access to the data. So the police didn't want to waste those unlock tries. They knew that there's no possible way they could get it in 10 tries. So they started speaking to some cybersecurity experts to see if there was some way to get access to the data without unlocking the phone. First, they went to Apple, and Apple said, we don't have the key. The only thing that has the key is the device itself, and there's no way to recover the key. The key is your unlock code, and if you don't type in the correct unlock code, it's just not going to work. And so I think they went to some other security companies, and some of them suggested one way to get access to the data would be to take the memory chips themselves, the flash memory chips, which are little rectangles about this big. They're encased in plastic, and so you could basically sand off the top layer of the plastic encasing the flash memory chip, exposing the flash memory device itself inside of that plastic case. And then you could hook up probes to that and then essentially read the data off. If you can read the data off, although it's encrypted, you could read the data off, and then you'd have as many tries as you needed to be able to decrypt it. You could run a program that basically would try to decrypt it, and when it succeeded, then it would be able to expose the data. But there were many dangers in doing that. One danger would be if you filed off just a little too much, you could damage the memory cells, and then that would render the data useless. You wouldn't be able to read the data off of it at all. And then if you didn't file enough of it off, then you wouldn't be able to access the data by sticking those probes on it. So you had to get just the right amount off, not too much, not too little. And if you made a mistake anywhere in there, the whole thing is busted. So I think they eventually did find a company that was able to find a back door into the phone, a way to get access to the data, essentially be able to unlock the phone without exhausting those 10 tries. And I don't know how the company, I don't have any details on how that worked. I presume maybe Apple has fixed that bug since then. But that's how eventually the FBI got into the phone, is they found a security company that was able to do it. They had found some kind of bug in the operating system of the phone and were able to unlock it. So that is a little bit about the symmetric key cryptography. And I guess I'll leave you with this, which is because the symmetric key cryptographic systems are fast, they're good for handling bulk data. See, what happens if you want to send a whole bunch of data and encrypt it is you basically divide it up into chunks. Small enough chunks that you can encrypt just one of those chunks, and then you move on to the next chunk and you encrypt that one, and then you move on to the next chunk, you encrypt that one, and then you just basically put them all together. And then you've got all the data divided up into these smaller pieces, but you don't have to encrypt the whole thing all at once. You can just encrypt portions of it. So let me do a quick little demonstration of AES. And I found this website online called aesencryption.net. And the way, this is basically a quick little demo of AES encryption. You just type in some text up here. You can say like good afternoon, known to us all, and then type in a key, the shared key that's going to be used to encrypt and decrypt the data. Let's type in something like pizza. And then last, you can choose the size of your chunks, 128-bit chunks, 192-bit chunks, or 256-bit chunks. 256 these days is the most common. So if I go over here to the right side, I'm going to click on Encrypt. And then down here, in this box, is the encrypted data. Now, normally it would just be 256 bits or so of seemingly random ones and zeros, but to display it on the screen, it has been encoded using base 64. This makes it so that it's visible and just uses printable characters that we can see on the screen. So this is the text that I wrote up here, but encrypted and then encoded in base 64. If I then take this text, I'm going to copy it and then paste it up here. And then I click on Decrypt over here. And I come back, we can see that it has restored the original text. So the same key is used to both encrypt and decrypt the data. I can paste any text in here I want. I could even take like a little bit of Python code like this and paste that in here. Then if I encrypt that, I get this long string of data. And then if I then copy that, paste that into this box, and then click on Decrypt, I get the original text back. So any text that you throw at it, it can then chunk it up, encrypt each chunk, and then turn that into one giant string of numbers. It can base 64 encode it so that we can see it on the screen, and that is the encrypted data. So a good encryption algorithm will essentially take text or any data. It could be an image, it could be, as you've seen, some program code, it could be anything, and it turns it into just a jumble of numbers. It's really hard to distinguish that jumble of numbers from just random numbers. Like if I encrypted some data and I got a string out, and then I just generated some random numbers and generated a string from that. If I ran some statistical analysis on it, like how often do the ones appear, how often do the zeros appear, how long are runs of zeros and ones, we should see that both the random data and the encrypted data kind of have the same distribution properties. And so what that means is that when you encrypt data, there's nothing in the encrypted data that would give an attacker a clue about what the decrypted text would look like. Like there's no structure to it that they can say, oh, this sequence of bits here is occurring more often than this other sequence of bits. So that must mean that this one is more common than this other one. And this one over here must mean that this is a commonly seen phrase or word inside of the text. It just turns it into just seemingly random ones and zeros. So you can't tell anything about the original text from it. So what if you wanted to break AES? What if you wanted to decode or decrypt some encrypted text that you stumbled across and you didn't know what the secret key was? So the first thing you'd have to establish is how big are the chunks? And that wouldn't be too difficult to figure out. I believe that there are some markers in the encrypted text to let it know when the chunks begin and end. So you could determine pretty quickly what the chunk size was. But then the real problem is, how can you figure out what that secret key is? See here, I just have 6 characters as my secret key. But my key can actually be up to 256 bits long. It can be up to the chunk size long. And so I could essentially choose a key that is 256, or I think about 32 characters long. And most of the time, the key that is chosen is not like a word or a phrase. It's just probably a random number, a totally random number, a 32 character random string of characters. And so since it's not a dictionary word, since it's not a phrase, since it's not, anything in any language that someone knows, you can't do anything like a dictionary attack. You can't use common phrases to figure out what the passcode is. You just have to guess. And you can use a technique called brute force to try to crack this key. You can try every possible 256-bit key until you stumble across the right one. And the question here is, how long would it take to guess a 256-bit key? Well, in order to figure that out, we would have to we'll figure out how many possible combinations is that. So there are 2 to the 256 possible combinations, and we can calculate that number. So 2 to the 256. Well, that doesn't look so bad. I mean, it's a big number, but it's not like a gigantic number. But still, that's the number of combinations that are in 2 to the 256. That's the number of 256-bit combinations. All we have to do is loop through all of those and try each one. The question is, did the 256-bit refer to the key size or the data chunk size? I think actually it's both. The key and the chunk size are related. So if you use a 128-bit chunk size, you're also going to be using a 128-bit key. If I remember my AES algorithm correctly. Okay, so we got 2 to the 256, and I think if I do that in a regular calculator, I get about 10 to the 77th, more or less, right? Approximately equal to. So how long would it take to run through all 10 to the 77th combinations? Well, let's assume that we threw a modern processor at it, which is like a 4 gigahertz, and maybe it's a quad-core processor, so it can do 16 billion calculations per second. But the AES algorithm can't be done in one single clock cycle. It might take, thousands or 10,000 clock cycles to do. So maybe let's say that it can do 1 million AES decryptions per second. The ballpark, right? Let's just say the fastest computer you can think of does 1 million checks of the key per second. So we have 10 to the 77th divided by 1 million. Then we want to figure out how long would that take. So let's divide it by 60, which is the number of seconds in a minute, and then divide by 60 again, which is the number of minutes in an hour, and then divide by 24, which is the number of hours in a day. And let's see what we get. So we'll do 2 to the, let's just do 10 to the 77th divided by 1 million, divided by 60, divided by 60, divided by 24. Oops, not 10 times 77, here we go. There we go. So we get about 10 to the 66th days. And if we divide that number by 365, we get about 10 to the 63rd years. So how long is that? Well, scientists think that the age of the universe is about 12 billion years old. So that's about 10 to the 9th. And we're looking at 10 to the 63rd. So not only is it like the entire age of the universe, it is that many, 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 many times. So it would take much, much, much more than the age of the universe to run through all the possible keys that this could be. And then you might say, well, what if we just, and this is one computer, like what if we put all the computational power of the planet at work on this? And Well, we would then have to like guesstimate how much computing power there is. You know, let's say my computer can do 1 million of decryptions per second, and let's say that there are, I don't know, 10 billion computers that can all do that simultaneously. So if we take this number and divide it by 10 billion, you know, we still have this enormous number, 10 to the 53rd years to run through all the combinations. So you can see why the police in that shooting case were like, you know, up against this problem. We're like, well, we can't even try to decrypt the data. It would take too long to stumble across the key for this. So for the time being, it seems that using something like AES to encrypt data is, you know, a good way to go. And I say for the time being because who knows what the future is going to bring as far as computation power. You know, maybe somehow we can get not only every computer involved in cracking this, but maybe every molecule on the planet can somehow be turned into a computer. You know, and then we're still looking at multiple ages of the universe to do this. So it's just a mind-bogglingly huge number that we're talking about. So let's go over some of the pros and cons of symmetric key cryptography versus public key cryptography, which is what we're getting into today. So in symmetric key, both parties share a common secret key. You've got Alice over here who wants to talk to Bob, and in order to do so, she needs to communicate that secret key over to Bob. But whenever two parties want to communicate and keep their conversation private, they always have to assume there's an adversary. We'll call the adversary Eve. Eve is eavesdropping on their conversation, and so Alice and Bob have to assume that there's a third party that's listening to anything they say. And if they have a shared common key, then Alice has a problem. How do I communicate that secret key to Bob without Alice obtaining it? And so this is called the key exchange problem. How do Alice and Bob keep Eve, the eavesdropper, from obtaining the key? Well, one idea might be, why don't Alice and Bob just encrypt the key? Then you got another problem. If you encrypt the key, then you've got a shared secret to use for that encryption. And then how do you communicate that key over to the other party? So whenever you're using symmetric key cryptography, you've got this fundamental kind of practical problem of how do the two parties exchange that private key so that they can start communicating. But symmetric key cryptography is usually faster to compute. There's often dedicated hardware in modern computers that can do something like AES very quickly. And therefore, symmetric key cryptography is useful for encrypting and decrypting what I would call bulk data. So you've got, and bulk may mean essentially larger than your key. So anything more than 256 bits, in the case of AES, has to be divided up into these smaller chunks, and then each chunk individually encrypted. So, but since it's very fast, AES is useful for that. By contrast, public key cryptography is different in that each party has a separate but related key. Think of a padlock that has a place to put two keys in. One key is used to lock the padlock, and the other key is used to unlock it. So the one of the keys cannot fill both roles. If you lock the lock with one key, that same key cannot be used to unlock it. You have to use the other one. It doesn't matter which one you use first. It's just that they have to go as a pair. So each key is separate, but they are related, mathematically related, so that one can be used to lock and one can be used to unlock. However, public key cryptography is slower and more complex to compute, and therefore it's typically used to encrypt only a small amount of data. Small meaning something smaller than the key's worth of data. However, public key cryptography solves the key exchange problem because there's two keys. One is kept with the sender and the other is given to the recipient. And since they operate in a pair, the fact that the recipient has one of the keys doesn't affect what the sender does with his or her key. So RSA, which is the one that we're going to study today, is actually an acronym for the three mathematicians that invented it. Their last names are Rivest, Shamir, and Edelman. And there's another one out there called ECC, which stands for Elliptic Curve Cryptography. It's more recent. RSA, I think, was developed in the 1980s. So you can look on Wikipedia to find out exactly when. And ECC is more current. It's more recent. See, here's the story behind RSA. A very brief story is that, again, it was invented like back in the 1980s, and it was initially patented by its creators, or at least the company that the creators work for. And the way a patent works in the United States, and mostly around the world, is when you patent something, you get the rights to be able to use that patent, and no one else can use the patent without working out some kind of arrangement with you. But in return, you have to publish how that patent works. So you can go to like the U.S. Patent Office website and you can search for patents, and there you can see patents and how they work. So the trade-off is you have to tell everyone how your patent works, and in return you get legal protection for being able to use it. And so RSA was published, and anyone could see how it works, but no one could use it without paying the RSA company some money for the license to be able to use it. Well, patents expire after a certain amount of time, about 15, 20 years or so, which is supposedly enough time for the patent holder to be able to use their patent and profit from it. So the patent for RSA expired in the mid-90s, and it became available for anyone to use. Remember, the algorithm had already been published, but now there were no longer any licensing or any usage limitations on it. Anyone could use RSA. And coincidentally, the mid-90s is also when the internet really started to take off. And what was needed at the time was a way to encrypt emails and websites and bank transactions. And it just so happened RSA comes along and is perfect for the job. So RSA is currently the predominant algorithm used to protect web transactions, but ECC, elliptic curve cryptography, is coming up slowly behind it, or quickly behind it. However, it too is patented. So we could look at the algorithm, see how it works, and eventually I think I will have to show you in this course, in a future iteration of this course, how it works. But right now, the only way to use ECC is to purchase a license to be able to use it. So some websites do use ECC. It is a little bit more secure than RSA. And by that I mean, RSA claims that if you have, let's say, a 1024-bit key that you're going to use, it's going to take, X amount of time for a computer to be able to break that key, to try all the combinations and crack it. ECC supposedly can do the same kind of the same time to crack a key in, let's say, 800 bits instead of 1024 bits. And so ECC presumably could use smaller keys and still have the same level of security. All encryption algorithms are breakable. Eventually you can run through all the combinations and find the key. You can stumble across it. It's just a matter of time. And we already showed how a 256-bit key can't be cracked in like Age of the Universe. How can you possibly crack a 1024-bit key in any reasonable amount of time? You actually can, because the key is not just a random number, it is a calculated number, and so there is a significantly smaller space of numbers to check. But still, it takes a long time to do. So ECC is up and coming. I just personally don't know much about it, and even though we could talk about it, it's still patented, and so we can't actually like implement it and turn it into a product of any sort. Anyway, I want to show you a quick little demonstration of like almost like real world RSA. And a student of mine a few years ago coded up this little website, and it's just an online tool, kind of like that AES encryption, right? Just an online little tool to generate RSA keys and then encrypt and decrypt some data. So the first thing we're going to do is choose how big the key is, and we can choose these numbers. I'm going to stick with 1024. I've discovered that if I use 4096, it takes too long to generate the keys. We'll be here for a few minutes as it generates the keys, and that's just not a good use of your time. So I'll choose 1024 bits. You also need to pick something called a public exponent, and you can either pick a default one, or you can select one of these random ones. And I might as well just pick one of these random ones, like this one here. And then I click on Generate Keys. And the first thing that RSA does is it picks some prime numbers. And real world prime numbers are quite big. You can see this one is 2 lines and a little bit long, so it's probably on the order of, I would say, 250 to 200 digits. Same thing for this other prime number, about the same length. And then the product of those two primes is, what's this, about 4.5 lines of digits long. So it's all three of these numbers are quite big. And then it has generated 2 keys, one called the private key and one called the public key. So one of these is used to encrypt the data, and the other one is used to decrypt the data. And when you generate RSA keys, this is what they actually look like. They're base 64 encoded, and then inside of each one of those blocks is the data about those keys. So they are just really big numbers, basically. Okay, so I'm going to flip over to the tab that says Encrypt and Decrypt. You paste in the key you want to use. So I'm going to take the public key, copy that, paste it up here, and then put in some text that I want to encrypt. And then click on Encrypt. And then down below, it shows the encrypted data. Here's the raw, down at the bottom, the raw binary numbers. And then above is the base 64 encoded equivalent to that. So I can take this text, I'm going to copy that, and I'm going to delete all this other stuff. I'm going to paste the ciphertext here into this box. And then now I have to go and fetch the other key to use to decrypt. So I'll use the private key for that. Copy. And then go over here and paste the key in. And then click on Encrypt Decrypt, and we get the original text back. So as long as the text is fairly small, and here it has to be smaller than 1024 bits, which I think is, let me think, well, we can figure this out. What is 1024 divided by 8? It has to be less than 128 characters long. So that's still a fairly generous amount of space to be able to encrypt something, but still, that's the limit, right? You can only do 128 characters, and that's it, no more. That's with a 1024-bit key. If you go up to the 2048 or 4096, then you've got a little bit more space, but still you've got this hard limit. You can't go anywhere past that. The way that the RSA works is it doesn't chunk up your data. You only get one chunk. It's the size of the key, and that's it. Okay, so let's talk about how RSA actually works. And before we do that, let's review some of the concepts that we learned over the last 2 weeks. The first one is coprime, or relatively prime. This means two numbers, let's call them A and B, share no common factors. Another way to state that mathematically is the greatest common divisor of A and B is equal to 1. That's the highest number that divides into both. Next is the, I need a little more space, I'm going to move this down. Next is the totient function. And that was the number of numbers less than some number n that are coprime to n. Just to review, the totient of 10 is the number of numbers less than 10 that are coprime to 10. So share no common factors with 10. And mathematically speaking, 1 is not considered to be a factor of a number. So you always get that one for free. You always get number 1 included in this list. But then 2 is not coprime with 10 because the factors of 10 are 2 and 5. So anything that's a multiple of 2 or 5 is not going to work. That leaves 3, 7, and 9 as the only 4 numbers that are coprime with n and less than n, and the number of those numbers is 4. The totient of 11 is easy to compute. 11 is prime, so every number less than 11 is coprime with it. So for prime numbers, it's easy to calculate the totient. You just subtract 1 and then you're done. And then the multiplicative inverse. That was defined as the number which, when multiplied by your first number, yields 1 mod n. So you're given one number, you're going to find another number which, when multiplied by the first number, gives you 1, but in modular arithmetic. So it's not going to be a fraction. It's not going to be like a partial decimal number. It's going to be an integer number, but in modular arithmetic, it's going to be equal to 1 when you multiply them together. So those are the concepts that we need to bring forward from what we talked about the last couple of weeks in order to be able to do RSA successfully. So let's go ahead and run through the algorithm. There's going to be a little bit of math involved here, and I'm going to need your help. So to kick this all off, we need to pick 2 prime numbers. We'll call them P and Q, 2 prime numbers. And the only stipulation is that they can't be equal to each other. Now, for our purposes, to keep the calculations relatively simple, let's stick to prime numbers that are less than 100. Otherwise, the numbers just get too crazy. So here's a list of prime numbers. On the first row, you can pick any number on the first row and any number on the second row. We just need 2 prime numbers that are different from each other that are less than 100. Tell me, give me some ideas of what I should use, and we'll go with it. So we just post something in the chat, post 2 numbers off this list, and we'll do all of our calculations based upon that. Anything? Okay, 31 is one of them. Okay, so we'll pick P is equal to 31, and we just need one more. One more in addition to 31. 41, we'll go with 41. So 31 and 41. We'll go with those two numbers. Okay, step number 2. Multiply those two numbers together. So 31 times 41, let me plug that into Python over here. 31 times 41, it gives us 1,271. So we'll call that number n, and this is going to be our modulus. When we do mod something in our encryption, that's the number that we're talking about. Step number 3, compute the totient of n. In this case, the totient of 1,271. Well, this is easy to do because we know that 1,271 is the product of 31 and 41. And one of the properties of the totient function says that if we have two prime factors, coprime factors of a number, we can just compute the totient of each one separately and then multiply the results together. And since each one of them is prime, we know that we can just subtract 1 from each, and we've got our answer. So we get 30 times 40, which is 1,200. And let me just double check my math and make sure I got that right. Yes, 1,200 is the totient of 1,271. Okay, step number 4. We are going to derive a number e, and this is not Euler's number, 2.718. Not that number. This is just some number e that's between 1 and the totient of n. So a number anywhere in the range of 2 to 1,199, and is coprime to 1,200. So we want to find a number between 2 and 1 less than 1,200 that is coprime to 1,200. And we can basically just use a loop to do this, or we can just generate a list of all the possible numbers and just pick one of them. So luckily we have Python on our side. We're going to ask Python to generate this list for us. So to be able to do this, you know that for something to be coprime means its greatest common divisor is 1. So we need a GCD function to use here. And there's one built in to Python in its math library. There's also the one that we've written ourselves using the Euclidean algorithm. I'm going to, just for speed's sake, I'm going to use the built-in one. So I'm going to say from math import GCD. And we also need our Computer Science 26 library so that we can do things like map and filter. So from CSCI 26, import star, and we're good to go. So now I can write a function that will determine if a number x is coprime with 1,200. Is coprime with 1,200 x. And that'll return true if the greatest common divisor of x and 1,200 is equal to 1. Let's try out some numbers. Is coprime with 1,200? Let's throw in like 100, and that says false because they do share at least one common factor, like 2 or 5. And let's try another number, coprime with 1,200. Let's put in 37, and that comes out to be true. And in this case, it's because 37 is prime, and prime is obviously not going to share any factors with some other number. So I now have a function called is coprime with 1,200, and now I can use my filter function. I'm going to start with a list of all the numbers between 1 and 1,200, and then filter out the ones that don't meet that criteria, and what I'll be left with is the ones that do meet the criteria. So we'll say filter is coprime with 1,200, range 2, 1200. So that'll start at 2 and go up to 1 less than 1200. And here's the list. It's a big list. These are all the numbers between 2 and 1200 that are coprime with 1200. And all we need to do is just pick any one of them. It's easier to see them if I get it to display it all as a block. So I'll just put print around this. And then we get this nice block of numbers. So these are all the numbers that are coprime with 1200. We just need to pick one of them. So take a look at the list. And what I'm going to do is I'm going to write on the iPad what we just did here on the screen. Take a look at the list, pick one of them. And, I'm going to write down here, somebody select, we should just pick 127. That looks like a good one. It's in the list. So all we got to do is just list out all the numbers, 7, 11, 13, 17, 19, 23, 29, 31, and then just pick one. So it looks like someone suggested do 127. So let's pick E equals 127. And then step number 5 is to calculate D, which is the multiplicative inverse of E. So we want to find a number, D, which when multiplied by 127 gives us 1 mod 1200. So we want to find E times D equals 1 mod 1200, which means 127 times D is equal to 1 mod 1200. And we have 3 ways that we can use to find the multiplicative inverse. So let's go over those 3 ways. One way is brute force. Just use a loop. Go from 2 up to 1200, try all the numbers and see which one, when multiplied by 127, gives us 1. Let's go ahead and do that. So we'll go for D in range 2, 1200. If 127 times D mod 1200 is equal to 1, just print it out. So we're going to run a loop from 2 to 1200. Check to see if when we multiply them together, mod 1200, we get 1. And then when we find 1, we'll just print it out. So the first one it finds, that'll be it. And it found 463. So just as a double check, if we do 127 times 463, we get 58,801. But if we then do mod 1200, we get 1. So we know that these two numbers are multiplicative inverses of each other. So here's what I wrote in Python. I went for D in range 2, 1200. If D times 127 mod 1200 is equal to 1, print D. And we came up with D equals 463. Okay, so that was one way to find the multiplicative inverse. Another way was to use Euler's theorem, and let's go over that one. And the third way is to use the extended Euclidean algorithm, and we'll go over that next. So technique number 2. Euler's theorem. So that one was a to the totient of m is equal to 1 mod m if a and m are coprime. Now, by itself, this is not useful to us, but if we divide both the right-hand side and the left-hand side by a, we get a to the totient of m divided by a equals a to the negative 1 mod m. And then we can rewrite that left-hand side to be just a totient of m minus 1 is equal to a to the minus 1 mod m. And this is an important derivation because this right-hand side is what we're trying to calculate. This is the definition of what the multiplicative inverse is. It is the reciprocal of a mod m, and we can calculate it this way. So the problem we're solving is to find the multiplicative inverse of 127 and 1200. Now we know the answer is going to be 463, but let's see if we can calculate it directly using this formula. So 127 is A and 1200 is M. So I'm going to plug 127 in for A, and I'm going to plug in 1200 for M, and we'll see what happens. So I'm doing 127 to the totient of 1200 minus 1 mod 1200. Now, you may be looking at me going, we already know what the totient is, right? We calculated on the previous page. Hold on just a moment. We calculated the totient of 1271, which was the product of P and Q, and we came up with 1200. So now we're trying to find the totient of 1200. We're essentially trying to find the totient of the totient. So this is a totally different number. We don't already have this number. We need to calculate it. How are we going to calculate the totient of 1200? Well, to calculate that, we need to factor this into its prime factors. Well, let's split it up. 1200 can be divided up into 12 and 100, and 12 can be divided into 3 and 4 can be split up into 2 and 2. So we've got 3, 2, and 2 so far. 100 is obviously 10 times 10, and 10 is 2 and 5, and this 10 is 2 and 5. So here are our prime factors: 3, 2, 2, 2, 5, 2, and 5. So we are trying to calculate the totient of 2 to the 1, 2, 3, 4, 2 to the 4th times 3 times 5 squared. Okay? So we have two prime factors, 2 and 5, that are each raised to a power, and we have one standalone prime factor. So for the ones that are raised to a power, we have a formula for calculating this. And remember, it was like a p minus 1 times p to the n minus 1. So basically you take the base, which is 2, and you subtract 1. and you multiply that by the base raised to the exponent minus 1. And then the 3 is easy to handle. That's just 3 minus 1 because it's prime. And then the 5 squared we'll handle the same way we did to the first one, the 2 to the 4th. This is 5 minus 1 times 5 to the 2 minus 1. All right, so this is 1 times 2 to the 3rd. And then this is 2 in the middle. And then this is 4 times 5 to the 1 power. Whew. So we got 8 times 2 times 20. And let's see, that's 16 times 20. 16 times 20 is 320. Let me just make sure I did that calculation right. So 8 times 2 times 20, 320. Good. So the totient of 1200 is 320. Okay, so what did we do there? We took this 1200 number right here, and we came over here and calculated that. And then this number 320 came back, and we're doing 127 to the 320 minus 1 power, mod 1200. So this 320 number came back and got plugged in right there. And let's try this out. So 127 raised to the 319th power. Whoa, that's a big number. But remember, we're doing mod 1200. And we get 463. All right. That is what we are looking for. I am always so relieved when this works out. So we did it using brute force, and we did it using Euler's theorem, and we got the same answer. So the only downside of using Euler's theorem is that we have to factor this number here. And factoring a number into its prime factors is actually a computationally expensive process. You basically just have to run a bunch of loops to find the factors, and once you find one of them, you move on to the next one, and you move on to the next one, and you keep going until you run out of numbers. So this is not the best way to do it. By far, the easiest and best way to do it is to use that extended Euclidean algorithm. So that one was number 3, use EGCD. So we're going to do EGCD of, what was it, 127 and 1200. Oh, I realize now that you couldn't see all the stuff that I was on the, was I, no, okay, I'm good. I was, for a moment there I was thinking, oh, you didn't see any of the calculations I just did, but you did. So here we are, we're calculating EGCD of 127 and 1200. Now I don't have that in here, so I got to go ahead and type that function in. So define, this is going entirely from memory. I hope I get it right. So if b is equal to 0, we're going to return 1, 0. Else, let's see, q equals a divided by b. We just want the quotient, the integer quotient. And then s and t is equal to e GCD of b and a mod b. And then finally, we're going to return t comma s times q, s minus q times t. Okay, if my memory serves correctly, that is the definition of the Euclidean, extended Euclidean algorithm. So let's go ahead and plug in our numbers. And we can look at that. 463. It's exactly what we wanted. So the first number that gets returned, it returns a pair of numbers. The first number, the x value, is the number that we want. Now, occasionally you do this and you get a negative number, but that's okay. You just do an additional mod 1200, and then it flips it over to the congruent positive number. So we got 463 from that. So it's returned 463, and what was it, negative 49, and this is the one that we want. So as I said, by far the extended Euclidean algorithm is the fastest way to compute the multiplicative inverse. This is the one that the actual RSA encryption and decryption algorithms in your computer actually does it. So it runs through all these calculations that I showed you here, picks prime numbers, multiplies them, finds the totient, finds a number that's coprime with the totient, finds the multiplicative inverse of that, and it uses the extended Euclidean algorithm to find that number. So really the hardest part about all of this is this step number 4, find a number that's coprime. And that is why in the demo that I did over here, there was, let me zoom in, there was a default. This number here, 65,537, happens to be used by quite a few implementations because it's a prime number. And it's nice because it's very close to 2 to the 16th, so it's very close to a power of 2, and it's a prime number. So very often the value of E is just simply chosen to be that number, and then D is calculated from that. But remember, we're talking about huge numbers here. Normally we're talking about just enormous numbers. So to find the multiplicative inverse of a number mod, some gigantic number, is going to take a fair amount of computation power. Even to do that extended Euclidean algorithm, it still takes quite a while to run through all those iterations of the process. And so that's what takes a while when you are choosing this key size here. Is if you make a bigger key size, the numbers are bigger, and it takes longer to calculate those numbers. It takes longer to find those multiplicative inverses. Okay, so where does that leave us? So we had 31 and 41 as our P and Q. We multiplied them together to get 1,271, and then we found the totient of that number. We picked a value for E that was coprime to 1200, and then we found its multiplicative inverse. So we got 6 numbers that we have calculated. Once you've calculated those 6 numbers, you then throw away P, Q, and the totient of N. So throw this one away, throw this one away, throw this one away, and keep the remaining 3 numbers. The reason why you want to throw away those numbers is they are used as the basis for all the calculations that were done. And so if somebody obtains those numbers, they would be able to then decrypt any message that you sent. So you definitely want to erase those numbers if you possibly can, if you want to keep things totally secure. Okay, so the RSA formulas are this. If you want to calculate a ciphertext, you take the plain text and you raise it to the E exponent, mod n. So that's the E here and the n here. And if you want to decrypt, if you want to obtain the plain text from the ciphertext, you raise it to the D power mod n. So those are the 2 formulas you need to know. And actually, they're the same formula. You just take, your value that you want to encrypt or decrypt, you raise it to the appropriate power, and then you just do a mod n at the end, and then you've got it. the pair of numbers E and N is one of the keys, and the other pair of numbers D and N is the other key. So encrypt with one, decrypt from the other. There's actually no requirement that you encrypt with E and you decrypt with D, although those letters happen to work out nicely. You could actually encrypt with D and you could decrypt with E, and it will still work as long as you use the other one to decrypt. Okay, whew, that was quite a bit of stuff, but we got through most of the math as far as calculating these numbers. And so when you want to have your web browser talk securely to a web server, or if you want to send a secure message using like WhatsApp or iMessage, or if you want to protect a bank transaction, a monetary transaction, then you definitely want to encrypt it using a technique like this. And your computer does all this work for you. Actually, if you've noticed, the very first time you visit a website, there's a little pause. Probably not that noticeable, 1 or 2 seconds. And what's happening during that pause is the client, your browser, and the web server are exchanging some information. They're talking to each other, getting the encryption all set up to go. So here's Alice and Bob. They want to talk to each other. So ahead of time, what both of them have done is they've gone through these calculations. Pick 2 prime numbers, and they're doing this independently of each other. So Alice and Bob actually have probably done this before they even know that they want to talk to each other. They probably did this when they first had this idea that they want to communicate with other people using RSA. So they'll go through and they'll calculate those 6 numbers. They'll keep the E, D, and N. So Alice will have what she calls her public key. And that public key, A pub, is made up of the E number, her E number, and her N number. And she's got another key called her private key, which we'll call A priv, which is made up of her D number and her N number. Bob also has a public and a private key made up of his E number and N number and D number and N number. So when Alice and Bob decide that they want to talk to each other, they then exchange public keys. Alice sends hers to Bob, Bob sends hers to Alice. How do they do this? Well, they're called public keys because they can be sent publicly. They can be sent without any encryption between them. Alice and Bob could shout them to each other. They could send each other emails with the numbers in them. They could publish them in a book. They could put them on a website. They could spray paint them on a wall somewhere. It doesn't matter how they convey that information to the other party. That information is considered to be public. And we can also assume that Eve, the eavesdropper, has also listened in and obtained those public keys. So Eve, the eavesdropper, has obtained copies of Alice and Bob's public keys. So now, Alice and Bob want to send messages. Alice wants to send Bob a message in such a way that only Bob can read it. What does she do? So Alice takes the plain text, and then she runs that plain text through which key? Which key does she use to encrypt this message that's going to Bob? So Alice wants to send a message to Bob so that only Bob can read it. Which key should she use? Now she's got 3 keys that she can use. She's got her private key and her public key, and she also has Bob's public key. She does not have Bob's private key. Bob has kept that private. So which of those 3 keys, her public key, her private key, or Bob's public key, should she use to encrypt this plain text so that only Bob can read it? Take a guess. Post your guess in the chat and see what we come up with. Or maybe it's not a guess. Try to reason your way through it. Try to reason your way, how would Bob decrypt this message? Can you figure it out? Yeah, you've got it. She would encrypt it with Bob's public key. So Alice is going to take Bob's public key and encrypt the message and send it over to Bob. And then Bob will take the ciphertext and decrypt it with which key? Which key will Bob use to decrypt the message and obtain the plaintext back? Can you figure that one out? Right, his private key. So Bob's private key would be used to decrypt the message and obtain the plaintext back. Great, figure that out. So let's see what would happen if Alice encrypted it using one of those other two keys. So what would happen if she encrypted it with her private key? If Alice encrypted the message with her private key, then the only key that could be used to decrypt it would be her public key. And that's fine. Bob has her public key, so Bob could decrypt the message. But the problem is, so does everyone else. It's a public key. They probably exchange the public keys by spray painting it on a billboard or shouting it to each other, which means that Eve, the eavesdropper, was able to obtain a copy of it. Anyone who has the public key is able to decrypt the message. So although Bob can decrypt the message because he has Alice's public key, so can everyone else. So it doesn't give you the level of security that you're looking for. It is encrypted, and if you don't have the public key, you can't decrypt it, but it's easy to obtain. All you have to do is ask Alice for it, or just go look to see where it's published and pick up a copy of it. So that's scenario number one. Scenario number two is, what if she encrypted it with her public key? If she encrypted the message with her public key, then the only key which could decrypt it would be her private key, and no one else has that. So no one else would be able to decrypt that message, and that makes it useless. So the best key to use would be Bob's public key. So what's the use of these other scenarios? Well, the second one I talked about of encrypting it with her public key isn't very useful, but the first one of encrypting it with her public key actually is useful. You see, encrypting the message with Bob's public key means that only Bob can read the message. That gives you security. It lets you know that only the recipient of the message is able to decode it, decrypt it. No one else can. That's a nice secure message. But what encrypting it with Alice's private key gives you is authenticity. You see, if it was encrypted using Alice's private key, then only Alice's public key would be able to decrypt it. Now, everyone has the public key, but they would know that only Alice would have been the person who could have encrypted that message, because it was encrypted with the only person who has that key. So encrypting it with Alice's public key, let me say it again, encrypting it with Alice's private key gives the message authenticity. We know that it's an authentic message, that it came from who it's supposed to have come from. So you can combine both those keys together and then get both security and authenticity. We can combine those two keys together so that Alice can encrypt a message so that only Bob can read it, and Bob knows that it could only have come from Alice. Now the question came up, what if Eve sends a message using the public key? Well, that's true, right? If you don't have that authenticity, then Bob is not able to tell that it came from Alice. Bob would think that it came from Alice, but in fact it came from, oh, actually, yeah, but it actually came from Eve. Right, so Eve encrypts a message using Bob's public key. Only Bob can decrypt it, but Bob has no idea who it actually came from. So combine those two features together, and then you have security and authenticity. And that's what actually happens on the web. Not exactly like that, but pretty close, that both keys are brought together and used to basically doubly encrypt the message. So you encrypt it once with one of the keys, and the result of that is encrypted again with another one of those keys. And so you get this doubly encrypted ciphertext. And then to decrypt it, you run it backwards through those corresponding complementary keys. And then you obtain the plain text, but you know that only you were the one who were able to decrypt it, and it must have come from the sender who sent it. Okay, so that's the scenario for how RSA is used in practice. We're going to go over more of that next time on Wednesday, but I want to leave you with this. Let's actually run some numbers through this algorithm and see if we're able to encrypt and decrypt it. So we had one of the keys. We had, well, let's say Alice wants to send Bob a message. So Bob has generated these keys. We've got B pub equals, I forgot what those numbers were. Oh, it was 127 and 1200. And Bob's private key is 463 and 1200. So let's take a plain text, and this just has to be a number, and the number has to be less than 1200. So you need kind of a random number to use to encrypt. Why don't we use, well, if you guys who are watching can come up with a number quickly, some number less than 1200, maybe 3 digits long, and we're going to attempt to encrypt it. I could do something like today's date, right? Today's March 7th. So maybe we can do 307. That's a March and then 7th. So that's going to be our plain text. So to calculate the ciphertext, we're going to take 307 and raise it to the 127th power mod 1200. Oh, you want to go with 289? I can go with that. We'll just back up. We'll just change that number. I came up with 307 off the top of my head. Well, I'll switch it. No problem. What did you say, 289? All right, we'll go with that. 289. Okay, 289 raised to the 127th power is this monster number, but we are doing it mod 1200, and that gives us 529. So 529 is the encrypted value for 289. So that's the number that we'll send over to Bob. So Alice did this. This is Alice. And now Bob is going to take over. So Bob will derive the plain text by doing 529 raised to the 463 power mod. Oops. Oh. I just see I did something wrong over here. Oh, let me see. Yeah. Whoops. I should be using this number here, 1271. Not this number. Remember we threw that one away? This is the number I'm supposed to use. So let me go back and change that. I'm glad I caught that before all these calculations fell apart. All right, now I need to redo it. 289 to the 127th power mod 1271. And we get 702. Okay, so I just swapped in the correct numbers on the screen, and now let's do this calculation. 702 raised to the 463rd power mod 1271. And we can see, first of all, that this number here is quite big. But we're going to do mod 1271, and if all goes well, if all of our calculations are correct, we should get 289 back from this. And we do. Excellent. There it is. And then we've got a suggestion to do the other number. Go ahead and do 307. So yeah, sure, go ahead. We'll do 307 raised to the 127th power, mod 1271, and we get 541. And then 541 raised to the 463rd power, mod 1271 is 307. So we can basically take any number between 0 and 1271, and we can encrypt it, and then we can decrypt it. So the number you encrypt has to be less than the value of n, but otherwise any value in that range should work. (307 to the 127th power) mod 1271 is equal to 541, and then P is equal to 541 raised to the 463 power mod 1271, and that gives us a 307 back. I know, it's like magic, huh? So the question you might be left with is, how do we really know it's encrypting? I can see like you're raising it to a power and then you're raising it to another power, but how do we know that it's really encrypted? In other words, how do we know that if I was to encrypt a whole bunch of data, that what I would get is basically random numbers out? It would appear to be random numbers. They're not, of course, they're not really random, right? They're calculated numbers, but if you didn't know what the keys were, they would be basically indistinguishable from just random ones and zeros. How do we know that this really is? I don't have a good proof for you right here, but be confident that mathematicians and computer scientists have been working at this for decades to try to make sure that RSA is as secure as it says it is, and no one really has found a way to break RSA without resorting to essentially brute force. Right? You can guess what the keys are. All you have to do is guess and check. Now, here's what I'll leave for you between now and Wednesday, which is, remember, Eve was eavesdropping in on the conversation. So Eve has the public keys. And the public keys are composed of two parts, one of the exponents and the modulus. So the question is, can Eve figure out what the private key is from the public key? So Eve has the public key, which can be composed of one of the exponents and the modulus. She also has samples of encrypted data because she's been listening in and she's seen the encrypted data go back and forth, so she's got samples of that. But to be able to decrypt it, she would need to be able to derive the private key from the public key. Can she do that? And that would be a question for you to figure out between now and Wednesday, is how can she do that? And is it easy to do? Now, you may know the answer to that last question. Of course, it's not easy to do. That's why RSA is secure. But how hard is it? It's not impossible. How hard is it? Can we kind of like put some kind of quantitative measurement on how hard it is to calculate the private key if you know the public key? Oh, good question. Python handles these large numbers gracefully, but how is it handled in other languages? So in other languages like Java, there's a library called big integer that would be used for something like this. And it's a library that essentially holds a number as not a sequence of ones and zeros, but actually as an array of bytes. An array, almost like an array of digits, the same way you would have done long division and long addition and long multiplication in your primary education. You learn to do it like column-wise, right? You know, with carries and borrows and things like that. So these libraries essentially do the calculations the way a grade school child does them. And so there are methods for doing add and divide and modulo, greatest common divisor, subtract, or exponent, and they're all built in. And so this is how the computer would deal with these large numbers. Now, even Python will eventually get bogged down by the size of these numbers. You know, these exponents get huge very quickly. If you throw a decent-sized exponent at it and a decent-sized plain text or ciphertext, you know, the numbers will just be too huge. Even though you're doing modular arithmetic, you're doing modulo some big number. And so even Python gets bogged down. And so there are ways to speed up the calculation. It has to do with the binary values of the base and the exponent and the modulus. You can do some fancy tricks with them, and you can speed up that calculation. But even with sufficiently large numbers, the calculation does still slow down. And that's why this algorithm is good for just encrypting a small amount of information, something that's smaller than the modulus, and only one of them. And so what happens in practice is both a symmetric key system like AES and a public key system like RSA are used in conjunction with each other to manage secure communications on the internet. So what happens is when you visit a website for the first time, your browser and the server exchange public keys. So remember, previously they've pre-calculated all these things. They exchange public keys. And now with the public keys exchanged, and remember they can do it out in plain text, so they don't have to encrypt it in any way. They just exchange their public keys. And now they're able to carry on a two-way conversation, but only small amounts of data. Okay, so the client and the server exchange public keys, and now they can use something like RSA to communicate with each other, but only small bits of data. So the next step then is to generate, each one of them generates a random 256-bit number. So the client generates a random number, and the server generates a random number. And then they use RSA to exchange those numbers. Right? The modulus is like 1024 bits or 2048 bits, but the number they're actually exchanging is only 256 bits, so it fits nicely within the bounds. So the RSA, the public key encryption system, is used to exchange those two 256-bit numbers, And then those numbers are used as the secret keys for a symmetric key system like AES. Okay, so let me run through that again. RSA, you exchange the public keys, and now you've got a two-way communication channel between the browser and the server. They use that once each to exchange two random numbers, and those become the secret keys for AES. And then from that point forward, your browser and the server use AES to send and receive data. So if you want to request a web page from the server, you take that request, you encrypt it using the server's AES key that you obtained. Then you send that request over to the server. The server decrypts it using its AES key. Remember, it's the same one on both sides. And then the server goes and fetches that resource and then encrypts it with your client's AES key, sends that over, and then your client decrypts it with the AES key. Okay, so RSA is used to exchange AES keys, and then AES is used from that point forward to manage all the communication between the client and the server. And so that's why there's that brief little pause the first time you visit a website, because all this stuff is happening. They're exchanging their keys, and they're generating random numbers, and they're exchanging those, and all that has to happen up front before any of the bulk communication, the sending of web pages, the sending of media and audio and whatever else is on that web page. All that has to happen before you can start sending those, the actual content of the page. So I said earlier that both those keys, the private and the public keys, get used to make sure the communication is both secure and authentic. It doesn't actually happen quite that way. There's something involved called digital certificates. We'll talk about that on Wednesday. What's a digital certificate? What's in the digital certificate? How is it used to manage communication between client and server? We'll talk about that on Wednesday. So I guess that's kind of it for today. We went through how to calculate the 6 numbers involved in RSA, how to use those 6 numbers, or 3 of the 6 numbers, to actually encrypt and decrypt data, and then an overview of how those numbers and how those algorithms are used to actually manage day-to-day, minute-to-minute, second-by-second communication between a web browser and a web server, or any other 2 parties that need to communicate on the internet. So on Wednesday, we're going to pick up where we left off. We're going to show some more like what's actually going on under the hood in RSA. What's a digital certificate? I mentioned that a moment ago. And also we'll start going over the programming assignment for this week. This will be one of like the last Python assignments you do. We're reaching kind of the crescendo of Python assignments because you're going to write a set of functions that will let you generate keys and encrypt some data and then send it over to one of your classmates, and then they'll be able to decrypt the data using your provided public key and then be able to decrypt it. So I'll have a discussion board where you can post encrypted messages, and then you'll be able to decrypt them and post your decrypted messages on the discussion board as well. And so that'll be on Wednesday. And then the following week, on Monday and Wednesday, really cool stuff, I'm going to show you something called hashing, which is called, it's kind of like encryption, but it's a one-way encryption. You can't decrypt a hash. You can only encrypt it. And what good is that, right? What good is hashing? Well, it's great for doing things like storing passwords or making sure that credit card numbers are correct. We'll also call it checksum. And so I'm going to show you how passwords get stored in a actual website database that holds things like usernames and passwords, how you authenticate users using a username and password, and then what happens if somebody obtains that list of all those encrypted passwords? Are they able to decrypt it? Now, I said a moment ago that the hashes can't be decrypted, but how do they actually break these passwords? And I'll show you that. I'll actually show you some of the tools that real professional password crackers use. And my goal in this is not necessarily to turn you into a password cracker, but to show you that really the technology behind it is not that complicated. The math behind it is not that difficult. And it's relatively easy to do, and it should help you see why you should be picking better passwords for your websites. Okay, let me catch up on the comments here. Yes, so the actual classes that I do for my students on Zoom are private classes, right? People have enrolled in my course, they've paid money to be there, and so when I'm doing my class, I'm primarily talking to them. Now, I missed my chance. I actually talked to them this morning, but I didn't record it. And so that's why I'm here now recording this. And the only people that are participating right now are just the YouTube folks. The Zoom people came and went, and they're done for the day. So I'm going to actually post the YouTube video for them to watch as well. Let's see. Oh, so the classes are always, this particular class is Mondays and Wednesdays at 9:30. And then I have another class Tuesdays and Thursdays, also at 9:30. That's my time, Pacific time. And that is a C programming course. And if you've looked through my YouTube channel, you can see there's kind of like two playlists that have a lot of videos on them. The C programming channel, C programming playlist, and the discrete structures playlist. And so I'm recording these live sessions and then posting them onto those two playlists. So I just kind of went over the schedule for the next week and a half in this course. And then that marks the end, the midway point of the first half of the course. Wait, that marks the end of the first half of the course. And then the second half of the course, the remaining 8 weeks, are going to be about a whole different set of topics. So we spent 8 weeks gearing up to be able to talk about encryption. And now we're going to switch over to doing things like sets, graph theory, combinations, permutations, finite state machines, regular expressions, language grammars, compilers, so a whole mishmash of other topics for the last half of the course. And that'll take us to about mid-May, I think. And that's when the course actually officially ends. What camera do I use? This is a Sony A6100, I think, is a model, along with a Sigma 30mm lens. That's what I'm using to do this. Very nice soft background, good light, much better than what I was using before. What I was using before was a Canon camcorder. You know, like what they call a prosumer one, like, you know, not just a really basic one, but not a professional one, somewhere in the middle. And it worked fine, but it was starting to show its age. It wasn't quite as sharp. And actually the HDMI connector on it was getting a little flaky, so every once in a while the video would just zap out and then come back. So I decided it was time to get another camera. And so I got this one about a year ago. And you're welcome for arranging this live class to talk about RSA. And like I said, we'll continue this conversation on Wednesday, and then we'll do really interesting stuff the following week on Monday and Wednesday. If this wasn't interesting enough, then next week will be absolutely fantastic. Okay, any other questions? I hope you can watch the streams at the usual time. I know this one was a little bit late today, and so I've potentially got almost a different audience because it's 3.5 hours later than it usually is. But hopefully, now that you know that I'm here, you can find my stream 3.5 hours earlier and watch it then. We get a great group of people in there who are actually interacting with me, and then as a result of your interaction, it's making the Zoom class more interesting. This is really great stuff. It's a great kind of like combination of the two together. You're surprised the audio is actually in sync with the video. That's because the audio is not taking the same route through the system as the video. Audio is a completely different track, and actually I think it is out of sync by just a little bit. And I don't have the time right now during the semester to fiddle with the audio sync, but maybe over the summer I'll be able to fiddle with that a little bit and get them really in sync. But right now, since they take two different paths through the system, that means the delay through the DSLR, the webcam, Doesn't match up quite with the delay in the audio, but they're pretty close. All right, I have to end this now. I've got to go run some errands, do some taking the kids around. So I had a great time. I hope you did too. And I will see you all on next time. That'll be Wednesday, 9:30. Take care. Bye-bye.